Hello, welcome to Algebra 2 1.04 notes. And today we're going to be talking about radicals. First thing we're going to do is focus on just our basic operations with radicals. So the first one is -2 times the square root of 125 minus 7 times the square root of 5. So whenever we are adding or subtracting, you must have the same number under the radical, or the same radicand. Must have the same radicand, which just means the number under the radical has to be the same. So 125 and 5, the numbers under the radical, the radicands, are not the same. So what we can do, though, is we can try to put this into simplest radical form. So when I do simplest radical form, I want to take the largest perfect square that I can from 125, and I want to write that first. If you forget your perfect squares, remember you can go to your y sub 1, type in x squared, and figure out what they actually are. Another helpful tip is to go to your y1 or your y2 and type in 125 divided by x. That'll show you your factors of 125, and then you can search for if there are any of those perfect squares listed in the table. In this case, you should see one at 5 and 25, and you want to put the perfect square first. So 25 is the perfect square, that gets written first, and 5 is not, so that gets written second. Then we're going to simplify. So the square root of 25 is 5. So the operation between the number, the radical, the other radical is all multiplication. So -2 times 5 is -10 rad 5 minus 7 rad 5. Now that we put this in simplest radical form, we do have the same radicands, so we can combine them. When you combine them now, you keep that radicand the same, so it stays radical 5, and you just combine the coefficients out in front. So -10 minus 7 would give us -17 times radical 5. Next step, number 2. 2 is a long one to write out at first, just to warn you, give yourself some space. So 2xy times the square root of 7x minus 7xy times the square root of 7 plus 12x times the square root of 7x minus 8xy times the square root of 7x minus 15xy square root of 7. So here we want to look underneath our radicals and make sure that there's no perfect squares under there. And it looks like they're all in simplest radical form at this point. So now we're really looking for, where do we have like terms? So we said we can only combine radicals if they have the same thing underneath the radical. So I see one here that has a radical 7x. I see another one that has rad 7x and another one. Not only do they have to have the same number under the radical, though, they have to have the exact same variables in front of the radical raised to the exact same exponents. So we're looking for any terms that have an x, a y, and then a radical 7x. So the next one has an xy, but just a rad 7, so that doesn't work. Next one has just an x on the outside. The next one has an x and a y and a rad 7x. So this one and this one are like terms. They both have x, y, rad 7x. Let's look at the second term. We have 7xy times rad 7. The next one's just an x, so that won't work. The last one is xy and a rad 7, so that one would also match up. Now we can combine them. So let's combine our greens. The variables and the radicals all stay the same. You're just combining the coefficients here. So 2 minus 8 gives you -6 xy rad 7x. Now I'm going to go to the blue set, with the squiggly set. And again, they have the xy rad 7 will stay the same. We're going to do our -7 minus 15 to get -22 xy radical 7. And then the last one we're just going to bring down, because there's nothing to combine that with, is 12x times rad 7x. And none of those can be combined any further, so that would be your final answer. Number 3 is 12 times rad 5 times 2 rad 10. So we're no longer adding and subtracting, now we're multiplying and dividing. So when you do that, you want to multiply your coefficients together, and you're going to multiply your radicals together. And you just multiply, keep the radical and multiply the radicands together, which is the number under your radical. So 12 times 2 gives us 24. And then under the radical, we'll have 5 times 10, which is 50. Now we need to put in simplest radical form. I always call that SRF, simplest radical form. If you don't know what that means, you should write it out into your notes. So we want to find the largest perfect square that we can take from 50. And again, you can use your calculator to help you. That should be 25 and 2. Simplify that. The square root of 25 is 5. It's all multiplication in between here. So 24 times 5 times rad 2, which would give me 120 rad 2 in simplest form. Let's look at a division problem. So 4 times the square root of 80 over 16 rad 2. When you're dividing, you want to divide the constants together, and then you're going to divide your radicals and reduce them. So 4 over 16, 4 goes into 4 once, 16 4 times. So now we're left with 1/4 for just that blue circle, our numbers. Then radical 80 divided by rad 2, you're just going to divide. So 80 divided by 2 is 40. So you're going to take your radical 40 and put it on the top because 80 is bigger. So the radical will go wherever the bigger number was. Now we want to put this in simplest radical form. So 40, I want to break into the largest perfect square, which would be 4 times 10 over 4. The square root of 4 is 2. So now I have 2 rad 10 over 4. And now I can reduce that 2 and the 4 since they're both non-radicals. 2 goes into 2 once and into 4 twice, leaving me with radical 10 over 2. And that can't be simplified any further. Next, we're going to throw in some variables here. So we're going to talk about radicals with variables. So one thing I want to point out at the beginning here is exponents. And I think I mentioned this in our other class as well when we were talking about dots. Exponents that are divisible by 2 are perfect squares. And we're going to talk in a couple minutes, if they're divisible by 3, they're perfect cubes. If they're divisible by 4, then they'd be a perfect fourth root. So to take the square root of an exponent, you're going to divide by 2 to take the square root. All right, let's do a couple practice. So we've got the square root of 3x to the 5th, and I want to put that in simplest radical form. So just like when we're doing it with just numbers, you're going to break it up into the perfect square first, and then the second radical is going to be your non-perfect square. So first I'm looking at the number 3. So 3 is not a perfect square, and there's no perfect square I can take from it. So I'm just going to put that whole 3 in the non-perfect square. Here, if you want to put a 1, you can. If you want to put nothing, that's fine too. Now I'm going to look at my x to the 5th. So like I said up here, if an exponent is divisible by 2, then it's a perfect square. Well, 5 is not divisible by 2. So you want to find the largest number that comes before 5 that is divisible by 2. So that would be 4. So I'm going to put x to the 4th in this radical. Now when you do radicals, so even if like the one we did before, if we do rad 25 times rad 2, we're doing that because we can multiply the numbers underneath the radical, the radicands, to get radical 50. So rad 25 times rad 2 gives us rad 50. So when we talk about our variables, we need to know x to the fourth times x to what power would give me x to the fifth, because we want to keep this x to the fifth, but we want to take out the largest perfect square, which is x to the fourth. So I want to know what has to be in my other radical, the non-perfect squares. So what you want to remember here is that when you're multiplying with the same base, you're going to add the exponent. So 4 plus what gives me 5? 4 plus 1. So that's just going to be x to the first power. Again, that's something you don't have to write the 1, but you can. Now I'm going to take the square root of x to the fourth. So you're just dividing 4 by 2, gives me x to the second, and bring down my rad 3x for my final answer there. Let's do another one. -4 times the square root of 50, a to the 8th, b to the 25th. So we're going to bring down our -4 and set up our two radicals. So the first one is all perfect squares. The second one is non-perfect squares. Start with your number, 50. What's the largest perfect square that you can take from 50? Well, I just did this as a practice one up there too, is 25 times 2. So together, these two radicals need to multiply to give you whatever's under the original. So 25 times 2 gives me 50. A to the 8th, is 8 even? Yes. So if it's even, then that tells us it's a perfect square. So I don't need to do anything. It's already a perfect square. So I'm just going to keep a to the 8th and put it in my perfect square radical. The next one sometimes throws people off because b to the 25th. 25 is a perfect square if it was the number 25. But if it's an exponent, so coefficient 25, I should say. But if it's an exponent of 25, then it's not a perfect square, because in order to be a perfect square, it has to be even. And 25 is not even. It's not divisible by 2. So we're going to take the number, the largest number before 25 that is divisible by 2. So that's going to be 24. So now you're asking yourself, b to the 24th times b to what power gives me b to the 25th? Again, keep your base, add your exponents. So that's going to be a b to the first. So that's going to go in my other set of parentheses, or set radical. I don't know why I keep calling them parentheses. Radical. All right, so now let's simplify. Again, multiplication is in between all of these because there's no sign that's written. So the square root of 25 is 5. The square root of a to the 8th, so you're taking 8 divided by 2 would give me 4. And then b to the 24th, I'm dividing 24 by 2, which would give me 12. And I'll leave my 2b underneath the radical. Now I'm just going to multiply together here. -4 times 5 is 20. A to the 4th, b to the 12th, rad 2b. And that's as far as we can take it. All right. Oops. I've got to work on my scrolling here. So number 7 is 7 times the square root of 27, a to the 9th, b to the 4th. So for this one, I want you guys to give it a try. Bring down your 7, set up, just kind of set it up for you. Set up your two radicals. Your first one's going to be all the perfect square numbers. The second one is going to be all your non-perfect squares. Pause the video, give it a try, and then check back for the answer. All right, so our answer to this one should be 21, a to the 4th, b to the 2nd, rad 3a. If you did not get that, then go back and look at the last couple that we've done, 5 and 6, and see where you might be going wrong. If you still can't figure it out, then you definitely want to reach out and let me know. Okay, number 8. Okay, simplify. So here we have another long one to write out, and it's actually going to be a little bit longer in terms of the work as well. So make sure you give yourself plenty of space. 7xy times the square root of 32x to the 5th, y to the 2nd, minus 3x squared, rad 27xy to the 7th, minus 11, rad 18x to the 6th, y to the 4th, plus 4y to the 3rd times the square root of 12x to the 5th, y. So I know this is a lot, but I want you to take it step by step. So first thing we're going to do is just simplify all of them. So then we can figure out what we're able to combine after that. So I'm going to bring this one, I'm going to make this my blue one. So I'm going to bring down my 7xy and set up my two radicals. And I'm just going to go through each one as we go. So 32, I'm breaking up 32 into the largest perfect square would be 16 and 2. Then I have x to the 5th. I want to take the largest even number that comes before 5, which would be x to the 4th, times x to the 1st. Y to the 2nd is already even, so that's going to stay y to the 2nd and go into my perfect square radical. Okay, next we're going to move on to this term. It's my red one here. You can't see the colors, a squiggly line. So keep my 3x squared, set up my two radicals. Largest perfect square I can take from 27 is 9 times 3. X to the first power, there's no even exponent I can take before 1, so that's just going to go straight into the second set. Y to the 7th, I want the largest perfect square that comes before 7, so the largest even number before 7 is 6, so y to the 6th times y to the 1st. Next we'll do 11, so kind of a spiky one. So negative 11, perfect square we can take from 18 is 9, 9 times 2. X to the 6th is already even, so it's already a perfect square. It's going to go in the first set. Y to the 4th, also even, is going to stay in our second set. And then the last one here, bring down our 4y to the 3rd, set up our two radicals. 12 can break down into 4 and 3. 4 is the perfect square, so that's written first. I can take x to the 4th from x to the 5th times x to the 1st. And y is not a perfect square, so that's going to go into our second set. Okay, so we've taken each one and we've just broken it down into the two radicals. So now on this blue one here, I'm just going to simplify and take the square root of the first radicals in each of them. So the square root of 16 is 4. Square root of x to the 4th is x to the 2nd. And square root of y squared is y. So let's write 2x. Minus 3x squared times the square root of 9 is 3. 6 divided by 2 is 3, so that's y to the 3rd. Times the square root of 3xy. Minus 11, square root of 9 is 3, square root of x to the 6th. 6 divided by 2 is 3, so that's x to the 3rd. And then y to the 4th, 4 divided by 2 is 2. Rad 2. And then our last term here, plus 4y to the 3rd, square root of 4 is 2. 4 divided by 2 is 2. Rad 3xy. And now I'm going to take it a step further, and I'm going to multiply everything we can that's in front of the radical. So 7 times 4 gives me 28. X to the 1st times x to the 2nd gives me x to the 3rd. Y to the 1st times y to the 1st gives me y to the 2nd. Bring down my rad 2x. So at this point, you should not, after that first step, you should not have any perfect squares underneath the radicals, the second radical. And so in the last step, that one radical in each color should not have any perfect squares underneath it. So this next one, we're going to multiply again. So 3 times 3 is 9, x squared times y to the 3rd, and leaving 3xy underneath. Going on to green, 11 times 3 is 33, keep my x to the 3rd, y to the 2nd, rad 2. And the last one, we have 4 times 2 is 8, x to the 2nd, y to the 3rd, those all stay, square root of 3xy. All right, now we're looking, we've put everything in simplest radical form. At this point, we're looking for where do we have like terms. So I'll start with my first one. I have an x to the third, y to the second, and a rad 2x. So I'm just going to go through each of these and see, do I have another one that has x to the third, y to the second, and rad 2x? So no, not the red. The green is really close, but there's not an x next to the 2 under the radical. So it's close, but not exactly, so it won't work. And the last one doesn't work. The exponents are wrong on the outside, are switched, and there's a y under the radical, so that won't work. So far, I'm just going to have to keep that 28 x to the third, y to the second, rad 2x. Now let's look at the red one. Do I have any that match that? So the green has the opposite exponents. That won't work. The black, so far so good, x squared, y to the third, and rad 3xy. So those two do match up. So I can add negative 9 plus 8 to get negative 1 x squared. So I can write the 1, but I don't have to. Y to the third, rad 3xy. And that means our green term here, negative 33 x to the third, y to the second, rad 2 also does not have a pair, just like the first one. None of those can be combined any further, so that's as far as you can take it. I know that was a long problem, a lot of steps, kind of combining everything we did before that. So look at it as much as you need to. All right, the next one, before actually we do number 9, I just want to write out some of your perfect cubes we're going to look at. So a perfect cube, as opposed to a perfect square, is when you're multiplying something by itself 3 times. So if you go to your y1 and type in x to the third, it'll list out all of your perfect cubes. So like 1 cubed is 1, 2 cubed, 8, 3 cubed, 27, 4 cubed, 64, 5 cubed, 125, 6 cubed, 216, 7 cubed, 8 cubed, 9 cubed, and 10 cubed. So these are ones you should start to recognize. And just like with your perfect squares, you should be able to recognize those. Something else that's important is about our exponents when we're talking about cube roots. Exponents that are divisible by 3 are perfect cubes. So in order to take the cube root, you would divide the exponent by 3 to take the cube root. And when you write a cube root symbol, it's your square root and the little 3 I want inside the hook. Because some of you start to get really big with those 3s and it looks like that, and then it starts to take over and it looks like you're doing 3 times that. So always put the 3 inside of the hook. So again, if you're looking for an exponent, let's say we do x squared times x squared times x squared. Keep the base, add your exponent. 2 plus 2 plus 2 is x to the 6th. So if I ask you to take the cube root of x to the 6th, I'm asking you what times itself would give you x to the 6th. So what you're doing is you're really just taking your exponent and dividing it by 3. Since we add to get it, we're adding it 3 times together. So you're going to divide your exponent by 3 to figure out the perfect cube. So it'd be x to the 2nd. Let's try a couple examples. So number 9, really basic. Let's just take the cube root of 16. We want to put it into simplest radical form. 16 is not a perfect cube. It is a perfect square. And that's where it's difficult because we've already worked so much with perfect squares in the last few years that your brain is kind of so focused on those, it's hard to transition to the cubes sometimes. So you want to, if you need to, write out your list or put it in your y equals so it's right there for you to look at. And then look to see here, I'll go lower than 16. The first one less than 16 in my list is 8. And 8 does go in evenly into 16. So again, I'm always going to write that one first. So it'd be the cube root of 8 times the cube root of 2. And the cube root of 8, so what times itself gives us 8 is 2. So 2 times the cube root of 2 would be in simplest radical form. Number 10, let's do the cube root of 250x to the third. So adding in a variable now. So I still want to do my number. So I'm still going to do the first set will be perfect cubes. The second would be non-perfect cubes. So 250, again, you can go to your y equals, type in 250 divided by x, and then look through to see which numbers we have from our perfect cube list. Or you could start by going to the number less than 250, which is 216, and then just see which one goes in evenly. So 216 does not go in evenly to 250, but 125 does. So 125 in the first set, 2 in the second set. X to the third. The exponent is divisible by 3, so that's a perfect cube, so it's going to go in the first set. Now take the cube root of this. So the cube root of 125 is 5. Cube root of x to the third is just x times the cube root of 2. Now, if you're not sure how to find the cube root, you can do it in your calculator too. So in your calculator, if you hit, there's a couple different options in the math menu. So if you go to math, you'll see there's a cube root option. There's an option where you can do any root you want. So you could even do 3, then math, and then choice number 5, which is like the xth root. And that would work as well. Or you can raise 125 to the 1/3 power is another way of doing it as well. All right, number 11, cube root of 128 times x to the 8th. So let's set up our 2 cube roots. We're looking for the largest perfect cube that goes into 128. So 125 does not, 64 does. So that's 64 times 2. 8 is not divisible by 3, so I need the largest number less than 8 that's divisible by 3. So 7, not divisible by 3. 6, yes, that's divisible by 3. So x to the 6 will go in the first set. So we're asking us x to the 6 times x to what power gives me x to the 8th, because I need these two radicals to always multiply to what's in the original. So remember, you keep your base, add your exponents. So 6 plus what gives you 8? 6 plus 2. So in here, we're going to have x squared. Now we'll take the cube root here. Again, you have them listed, so you should know off the top of your head it's 4, but if not, again, you could do 64 raised to the 1/4 power, or 1/3 power rather, or you could do the cube root 64 in that math menu in your calculator. So that's 4. To take the cube root of 6, you're going to divide it by 3, and 6 divided by 3 is 2, and then we just bring down the cube root of 2x squared. And the last one we're going to do is the 4th root. Just throw that in there for fun. 4th root of 16x to the 8th. So here you're taking the 4th root. Again, you can go to, you would type in 4, then go to math, then number 5. And then you could type in your 16. So the 4th root of 16 is 2, and 8 is divisible by 4. So that would be a perfect 4th root. So 8 divided by 4 is 2, so the answer would just be 2x squared. All right, and that is it for your radicals. I hope you had a radical time, and hopefully I will see you guys soon. Pi out.